Well, NMR spectroscopy is the Cadillac of spectroscopy techniques for nanostructure determination. There's still quite a bit of useful information, particularly about functional groups, that can be obtained from infrared spectroscopy. Infrared spectroscopy uses energy that causes molecular vibration. And the stronger the bond, the more energy is required. The unit that's used for infrared spectroscopy is mu bar, with a little tilde over it, which is called wave numbers. And a wave number is simply 1 over lambda, right? Where mu, the frequency, is equal to c over lambda. In hertz, or seconds to the minus 1, the wave number, 1 over lambda, is given in reciprocal centimeters. And typically, in the IR spectrum, we will look in the range from 400 reciprocal centimeters to 1,000 reciprocal centimeters. So we have our high energy here, and our low energy here. The stronger bonds will appear on the left-hand side and the weaker bonds on the right-hand side. And we generally look at percent transmittance. Rather than the more common absorbance that you're used to looking at for UV and visible spectroscopy. So 0% transmittance on the bottom, 100% transmittance at the top. If that wavelength of light is not absorbed, we should see a baseline that's at the top. And then we'll see dips. We call them peaks, but they are in fact troughs. And we'll see a peak where a large amount of light is absorbed. It tells us we've got a bond that has the strength that can only be vibrated by this high energy peak. The region from 2,000 to 4,000 reciprocal centimeters is typically where you'll see bonds stretching. And then the region down between 400 and about 1,700, known as the fingerprint region. Has stretching vibrations for lower energy bonds, but then it also has bending vibrations as well. And it always takes less energy to bend something than it does to stretch it. It's much easier to bend your arm here than it is to stretch it out and dislocate your elbow. So we're going to look at this region. You've already used the infrared spectrum, and so you already have had a sense for where some of these peaks show up. The vibrations can be modeled by thinking of a spring connecting the two atoms. And the energy, or in this case, the wave numbers, right, which is 1 over centimeters, follows Hooke's law, which says that the number of wave numbers is be equal to some constant times the square root of a force constant which is proportional to the strength spring, or in our case, the bond, we're treating it as if it's two atoms of a ball attached by a spring. So this force constant F should be proportional to the center of the spring. These are the masses of the two atoms. M1 plus M2 over M1, M2 is the reduced mass. So it's a constant times the force, or the square root of the force constant for the spring times the reduced mass of the two atom system that's attached to it. So if we know the relative strengths of bonds, we can predict their relative location on the IR spectrum. Not the absolute location, but certainly the relative location. For alkanes, which typically have both CH3 and CH2 groups, we can identify a bunch of different types of vibration. For a three-atom system like a CH2 group, where you have a bond angle that's not 180 degrees, might be 109.5 degrees if this is your typical CH2 group, we can identify a symmetric stretching which would have both of the CH2, or both of the carbon-hydrogen bonds lengthening and contracting in phase, like this. That's a symmetric stretching. Or we can identify asymmetric stretching. Which will have one carbon lengthening while the other one shortens. And then the opposite. Asymmetric stretching would look like this. One of the rules of IR spectroscopy is for the light to be absorbed, you must have both an energy that matches for the vibrational levels, and must cause a dipole moment change. So if you had a linear molecule, like carbon dioxide, for example, the symmetric stretching would not be visible in the IR because the dipole moment is 0 for both of these situations. So if the two oxygens go in phase, there's going to be no visible band. The asymmetric stretching, on the other hand, would cause a dipole moment change because now the dipole moment for this bond that's lengthened would be much larger than for this bond that's short. So not every IR vibration is actually visible in the IR spectrum. Really symmetrical systems, when they stretch and expand and contract, won't necessarily be visible. But since this is a bent system with a 109.5 degree bond angle, both the symmetric and the asymmetric stretching modes do cause a dipole moment change, and we should see those differences. For ordinary alkane sp3ch bonds, we see this carbon-hydrogen stretch somewhere from about 2850 to 2980 reciprocal centimeters. So kind of centered around 2900 and not as far up as 3000. For an sp2CH bond, because the greater amount of S character makes the orbital shorter and therefore the bond stronger, we would expect to see the CH stretch above 3000, usually from about 3050, 3150 reciprocal centimeters. And for an sp-CH bond in alkyne, we see that CH stretch at more like 3,300 reciprocal centimeters. And it's a strong and relatively sharp peak. There is more of a difference between the SP and the sp2CH bond stretching frequency or wave number than there is between the sp2 and sp3. And that's consistent with what you already know about acidity, where there's much less difference in the acidity of an sp2CH versus an sp3CH than there is between an sp-CH, which is all the way down to 25, 50, 44, 25, respectively. So there's a much bigger difference. The alkyne CH stretch is quite distinct. For plain old alkanes, in addition to the stretching, there are several different bending modes. There are in-plane and out-of-plane bending modes. I'm going to illustrate it again for CH2 group. An in-plane symmetrical bending mode, which is called scissoring, we'll take the two hydrogens and expand and contract them. Right? So we'll change that bond angle like this. That's a scissoring mode, where the hydrogens are moving in the plane containing the two hydrogens like carbon, and there's an in-plane asymmetrical, which is referred to as rocking, where both hydrogens are moved to the right and to the left. So the rocking mode looks like this, waving back and forth. And then out of plane, you have a symmetrical out of plane, which is called wagging. Symmetrical out of plane. Symmetrical out of plane is called twisting. What's happening is one of those is going in and the other one is going out, so there's twisting. We'll illustrate kind of the back end of the arrow and the point of the arrow. So the point of the arrow is pointing out to the back end of the arrow is going back in. And then there's an asymmetrical out of plane, which is called wagging, where two hydrogens would go in and out respectively like this, whereas the carbon is moving back and forth in the opposite directions of the hydrogens. So we've got scissoring, which is a symmetrical in plane. We've got twisting, which is a symmetrical out of plane. We've got rocking, which is asymmetrical in plane. And then we've got wagging, which is an asymmetrical in plane. All of those can theoretically have different frequencies, but two that are important that you see in many alkanes are CH2 scissors at about 1450 reciprocal centimeters, very common. You see it in large high intensity, if you have a lot of CH2s like you saw in tribristin, and a CH3 rock, which usually occurs in about 13 feet reciprocal centimeters. And you saw that in tribristin as well, but not as intense because there are only 3 CH3 groups, so there's a lot of CH2 groups. So for plain old alkanes, you're generally looking for the CH2 scissor and CH3 rock in that fingerprint region, and then you're looking for this CH stretch in the region around 2900, but not going over 3000. If you go over 3000, then you know you have either an alkene or an aromatic compound present. If you see a peak at 3300, it might be an alkene, or an alkyne rather, but it could also be an alcohol. The OH stretch shows up in a very similar region as the SPCH stretch. The OH stretch, however, is broad. It's very strong because it's a polar bond, which means there's a large dipole change, and it can show up anywhere between about 3200 and 3650 reciprocal centimeters. So kind of centered in the same region as where you see the SPCH stretch. The SPCH stretch is a very sharp peak, and the OH stretch is a very broad peak. The OH becomes even broader if it's on a carboxylic acid. If it's on a carboxylic acid, the OH stretch, because of some greater levels of hydrogen bonding and hydrogen exchange, you can see a peak that extends all the way from maybe 2500 to 3500, and pretty much engulfs that entire stretching region of the NMR spectrum. It's very distinctive when you have a carboxylic acid. NH stretches for primary amines or secondary amines show up in the region around 3400. There's a table that tells you the approximate locations. Table 11.4 on page 462. It will tell you a lot of the same information that I'm giving here. So for the amines, typically between about 3250 and maybe 3500 reciprocal centimeters. You'll see just one peak for a secondary amine, and you'll see 2 peaks for a primary amine, because for the secondary amine, you don't have 2 stretching modes. All you have is a single stretch. Add the second hydrogen, and now you get separate peaks for the symmetric stretch and the asymmetric stretch. So you can tell whether it's a primary or a secondary amine. If it's a tertiary amine, then there's no NH stretch at all. And you have to find out that there was an amine present using alternative methods. So you'll notice that in general, carbon-hydrogen stretches require less energy than nitrogen-hydrogen stretches, and nitrogen-hydrogen stretches require less energy than oxygen-hydrogen stretches. Because as you go from carbon to nitrogen to oxygen, you gradually get a bigger nucleus, which means you have a greater hold on the electrons, right? The more electronegative development causes a higher energy peak. But that's confounded by the hybridization issue. The S character can also affect it. All of those are fairly intense because hydrogen is a very small atom. And because it's a small atom, the bonds are short and strong. Bonds between 2 heteroatoms, even if they're multiple bonds, because the atoms are both fairly large, are generally less energetic. Nitrides and alkyne CC stretch or CN stretches are very distinctive because nothing else shows up in the region between around 2100 and 2200 reciprocal centimeters where you would expect to see alkynes and nitrides. Because nitrogen has a bigger nucleus, it's a slightly shorter, stronger bond, you typically see that one a little further up. Carbon-carbon bonds and carbon-oxygen double bonds show up at around 1700, 1745, high end of that region. Ketones and aldehydes typically on the lower end of that region. So you might say ketones and aldehydes are typically around 1720 or so, and esters around 1735 or so, so you can usually tell the difference. And amides, in fact, are typically more like 1680. So the carbon-oxygen double bond can allow you to tell not only that it's present, all strong peaks, because there's a large dipole moment change, not only that it's present, but also what type of carbon-oxygen bond is present. Carbon-carbon double bonds are typically around 1600 to 1650. And if it's a benzene ring, because you've got that resonance that makes the carbon-carbon bond partially double and partially single, you see two peaks at around 1500 reciprocal centimeters and 1600 reciprocal centimeters. And that's the ring breathing. It's the whole ring kind of expanding and contracting and expanding and contracting like a pair of bubbles. You'll only see one peak if it's CC double bond from an alkene. You'll see distinctly those two peaks at 1500 and 1600. And in both cases, you should also see that peak at about 3050 for the sp2-CH bond. So those are distinctive peaks that you can identify. Carbon-carbon single bond stretches, carbon-nitrogen single bond stretches, those are typically not going to be useful because they're buried in the fingerprint region where they don't do you much good. There are a couple of other peaks that are listed in the table, but the ones that I put on there are kind of the ones that are most diagnostic. In the fingerprint region, though, and hiding on the bottom of page 463 in the margin notes, are some very useful bending modes that will allow you to tell what the substitution pattern is around an alkene. So a vinyl will show two peaks, and those peaks will be about 910 and 990 reciprocal centimeters. Because you've got a cis and a trans hydrogen, you'll see two peaks. A trans arrangement on the disubstituted double bond generally shows one peak between about 950 and 970. A cis double bond generally shows one peak around 700 to 720 reciprocal centimeters. A general substitution pattern shows a single peak at about 890 reciprocal centimeters, and a tri-substituted double bond generally shows a single peak at about 800. So one peak at around 700, evidence of a cis double bond, one peak at around 800, tri-substituted, one peak at about 900-ish, geminal, one peak kind of getting closer to 950 to 1,000, trans, and then when you see two peaks, one close to 900 and one close to 1,000, then it's an evidence that you have a vinyl peak. That can be very useful because sometimes it's difficult to tell what the substitution pattern is, the difference between a cis and a trans double bond, for example, in ProtonMR. The coupling constant is different, right? 12 to 16 hertz for this one, 6 to 10 hertz for that one. But if you don't have very good resolution, sometimes it's hard to measure the coupling constant very accurately. There's another set of bending modes that are very useful for aromatic compounds. And if you skip ahead to chapter 15, I'll find it for you. There's a section that talks about NMR spectroscopy of aromatic compounds and IR spectroscopy. So on page 675, bending modes for aromatic compounds. And you'll discover that a monosubstituted benzene has two peaks, somewhere between 690 and 710, and then the second peak between about 750 and 770. What we call an ortho disubstituted pattern has a single peak between about 735 to 770. Para-substituted or 1,4 substituted system typically has a single peak, but it's between 790 and 840. So distinctly different for a 1,2 substitution versus a 1,4 substitution pattern, and then a 1,3 substitution pattern or a meta will again show two peaks. And those peaks will be roughly the same location, 690 to 710, which is an identical place to the monosubstituted, and then 750 to 810 for the second peak. It's typically not possible to distinctively tell the difference between a monosubstituted and a meta-substituted because these two peaks are about the same location as these two peaks, but you can tell the difference between monosubstituted and meta-substituted in another region of the IR spectrum, which I'll point out when I actually show you some examples. Para and ortho substitution you see kind of distinctive because they're very different. Around about 800 or a little higher than 800, whereas this one's closer to like 750. So the bending modes can be very useful for alkenes and for aromatic compounds in giving you more information about the actual substitution pattern. So that's it for theory on IR and on NMR. The only way to become good at actually interpreting these spectra is to look at a lot of spectra and get good at recognizing various patterns. So there'll be a series of videos where I put up spectra